Hello, my name is Anthony Quinn. I'm a professor in electronic and electrical engineering in Trinity College Dublin, and it's my pleasure to provide this very brief introduction to my Level 9 10 ECTS module in Statistical Signal Processing 5C3. It's a module that will certainly appeal to students who have had an interest in signal and system analysis, in probability and inference techniques, modules such as 3C1, 3E3, and 4C5, but I very regularly welcome students from other areas of the university and indeed many of our visiting students as well. So the module is concerned with design principles for recursive or online signal processing and also addresses some key paradigm problems in machine learning. And our concern really is that the design of these algorithms be consistent with our knowledge of how the data were generated in the first place, the context in which we are undertaking our algorithmic design. So for this purpose, I champion the fully probabilistic approach to the quantification and manipulation of uncertainty, what we call the Bayesian approach. But we're careful amid that universal framework to specialize to some of the really important classical criteria for the design of some very important algorithms in signal processing: likelihood-based approaches, maximum likelihood estimation, geometric approaches, least squares estimation, and the minimum mean squared error criterion of Wiener for optimal filter design. But this Bayesian approach is important in providing us with an auditing framework, which essentially forces us to travel through all the assumptions that we are making about the data sets that we're studying. And then in many ways, non-optionally, if you like, in a prescriptive pathway, this leads to algorithmic design that has optimality properties and consistency properties. And we lean heavily on very flexible model structures, models that can be applied very widely, notably linear regression structures and various autoregressive structures. And along this pathway, we encounter some of the really important algorithms that have been implemented in practice and, as I say, very widely across applications. The Wiener filter and the Kalman filter and their various predictor variants. And in understanding them in this Bayesian framework, we also become aware of their limitations and the limiting assumptions under which they were designed. And in some ways, this is an invitation to evolve them, a sort of a research invitation, as is appropriate, I suppose, for a module that is research informed. And another principal concern of the module is with what I would coin responsible inference. So we're concerned with understanding and quantifying the uncertainties associated with our decisions. While we can claim that our decisions are optimal, we never lose sight of the fact that they are uncertain. And one of the important emphases of the course is on comparing alternative model structures and criticizing and comparing them in terms of their suitability for the problems that we're studying. Implementation is a key concern. I've already mentioned that really it's a course in the design of real-time online signal processing algorithms. And so in parallel with the classroom-based work, I run a MATLAB-based laboratory program in which we implement the various algorithms and explore their variants, particularly in terms of their statistical performance, both with simulation data sets and with real data. So the module is fully described there in the module descriptor up on the school website. The objectives and philosophy of the course are fully expressed there, but otherwise my email address is at the bottom of that page there, and I would be delighted to discuss the module further with students who might be interested in taking it. And I hope that I'll see many of you in class next year. Thank you very much. Bye-bye.